The first major concept in calculus is that of the limit. Now, limit is a value that something approaches, and we're going to look at limits from both a graphical and numerical standpoint in both real and theoretical situations. Let's start our discussion with limits with an informal definition of a limit. What a limit is, it's taken as the input of the function x approaches some value from either side. In this case, x is approaching the number c from both the left side and the right side. And the limit is the value of the function as x approaches c from the left and the right. So if f of x becomes closer and closer to a single number L as we approach that number c from the left and the right, then the limit of f of x as x approaches c is L. This is the notation of the limit. The limit of f of x as x approaches c is L. That's how we read it. We're going to look at evaluating limits in three different ways. Graphically, by making a picture; numerically, by making a table of numbers; and analytically. In this lesson, we're going to look at the first two. Let's take the function f of x equals x squared plus 2x minus 2. Now this is a continuous function, and we want to find the limit of f of x as x approaches 2. So we're looking for what the limit is as x approaches this point from the left side and the right side. And it appears, as the function approaches 2 from the left side, it appears to be going to 6. As the function approaches 2 from the right side, it also appears to be going 6 to 6. So we would say that the limit of f of x as x approaches 2 is 6. Now let's look at the same function where x is not allowed to equal 2. This is a parabola with a hole at the point 2, 6. The function has no value at the point x equals 2. If we want to evaluate the limit of this f of x as x approaches 2, we're going to look from the left-hand side, and as we go up this parabola, we notice that as we approach 2, f of x indeed does approach 6. So from the left-hand side, the limit is 6. If we go from the right-hand side, it appears the function also approaches 6. So the limit of f of x as x approaches 2 is 6. Notice the function had no value at x equals 2. That doesn't matter. What matters is what's happening as we approach from the left and the right-hand sides. The existence of a limit at a given point is independent of whether the function is actually defined at that point. Instead, it's what's happening as the function approaches that point. So let's kind of put it all together in an informal definition. If f of x becomes closer and closer to a single number, L, as x approaches c from both the left and the right, the limit of f of x as x approaches c is L. But very, very critical point. The existence or non-existence of the function at x equals c does not matter. It's what's happening as we approach the left and the right. As we just saw, function where it had no value at that c point, but it still had a limit. Boring function f of x equals 2, x not equal to 1. The limit of f of x on this function is 2, even though f of 1 is undefined. As we approach the function from the left, it's 2. As we approach the function from the right, the limit is also 2. Therefore, the limit f of x as x approaches 1 is equal to 2. Here's a function that has a completely different value at x equals 1. And again, this brings home that important point that what the function is doing exactly at the point does not matter with regard to a limit. This is a step function, a piecewise function. F of x is defined as 2 for all points except where x equals 1. At x equals 1, the value of the function is 4. The limit of this function as x approaches 1 is equal to 2. As we approach from the left, as we approach from the right, we're still at 2. It doesn't matter that the function is 4. That has no bearing on what the actual limit is. Now let's evaluate limits graphically. We're going to make a picture to find the limit. So let's look at the function f of x equals x squared plus 4x plus 3 over x plus 1, a rational function. And this rational function is undefined as at x equals -1. You'll recall from pre-calculus because the denominator goes to 0. It is not a vertical asymptote. It's a point discontinuity or a hole. This rational function winds up being a straight line function with a point discontinuity or hole at x equals -1. Well, suppose we want to find the limit at x equals -1. We're going to approach -1, x equals -1 from the left-hand side. We're going to approach x equals -1 from the right-hand side. And you'll notice in both cases we're approaching the value f of x equals 2. Whether we go from the left or the right, we're still getting closer and closer to that value of 2. So we would say that even though the function has no value at x equals -1, the limit of the function as x approaches -1 is equal to 2. Now let's look at evaluating limits numerically. When we evaluate things numerically, we're going to make a table. So let's look at the rational function f of x equals x to the third minus 1 over x minus 1. And of course, x can't be 1 because that becomes a point discontinuity. So we're going to approach it from the left numerically, we're going to approach it from the right numerically, and see if we're approaching a specific value. And whatever that number is going to be the limit. So what we're going to do numerically is make a table. We're going to take values of x that get closer and closer to that x equals c of 1. There's no rule about what you should do, but you need to get values that get closer and closer and closer so that you can see if there's a pattern. And so what I'm going to do here, we're going to go 0.8, 0.9, 0.99, and 0.999. Each time we're getting an order of magnitude closer, 0.01 and then 0.001, a tenth, a hundredth, and then a thousandth away from 1. And we do the same thing on the right-hand side. So this is the left-hand side, this is the right-hand side. And really we're doing the same thing graphically. So when we evaluate f of x at these values of x, we start to see a pattern. When we look from the left-hand side, we can see the numbers steadily increasing, getting closer to what looks like 3. Let's confirm that by going down from the right side. Now the numbers are steadily decreasing, but they appear to be converging on the number 3. This is clear enough evidence to see that the limit as x approaches 1, as we go from both the left-hand side and the right-hand side of the function, is 3. So now let's look at limits that fail to exist. And there are 3 cases of when limits fail to exist. And we're going to look at each one of those cases. First, if it approaches a different number from the right side and approaches a different number from the left side, 2 different numbers from the right and left sides as we approach c, the limit doesn't exist. If the function increases or decreases without bound as x approaches c from either side, the limit doesn't exist. And if it oscillates between 2 numbers, it also fails to exist. Again, the core definition of a limit is it's got to approach the same number from the left and the right-hand side. So let's look at the graphical examples of these cases. Here's the function absolute value of x over x. The function is undefined at 0 because the denominator goes to 0. When we approach that function from the right-hand side, the limit appears to be 1. When we approach that function from the left-hand side, though, the limit appears to be -1. So therefore, the limit does not exist because we've got different behavior on the right side and the left side. Let's look at the case where the function increases or decreases without bound. So here's a function f of x equals 2 over x minus 3, another rational function. If we approach it from the left-hand side and we're approaching the value of x equals 3, the function is undefined at 3 because the denominator goes to 0. And this is a vertical asymptote. Approaching 3 from the right, f of x increases without bound. We go on up to positive infinity. Approaching 3 from the left, f of x decreases without bound. So if either of these things happened, that would be enough to declare that the limit fails to exist because the function increases or decreases without bound. You could put DNE, does not exist for short. Let's look at the final case of oscillating behavior where a function goes between two different values back and forth continuously and never actually reaches a limit. So let's look at the function, the limit of sine of 1 over x as x approaches 0. Let's look at this graphically. And this is a fascinating function. And here's a look at it from negative pi to pi. And you can see as we approach 0 from the left-hand side, there's just this blur. And as we approach 0 from the right-hand side, we see the same blur. So let's zoom in and see if we can get a better picture of what's going on. So when we zoom in, we still see the same blur. And we see it over and over again. Just more of a blur. And what's happening is it's oscillating between two numbers. So we've looked at limits from a graphical and numerical standpoint after defining what a limit is informally. And hopefully at the end of this now you understand what a limit is and how to determine it both graphically by making a picture and numerically. And you'll also understand when limits do and don't exist.